Okay, so yeah, welcome back to the CS580. So last time we were discussing some of the ideas about the reflection the models, with some slightly more details about the BRDF and also some of the ideas in terms of like how we also incorporate not only the reflection but also the transmission of the light as well. We discussed some kind of the basic ideas in terms of like how we also compute the proportion of the light to be reflected and be reflected. So that was kind of the idea of the Fresnel the equation, and based on that we can basically compute some kind of the coefficients for that. And also we discussed some kind of the ideas in terms of how we can also compute some kind of the proportion of like those things for the thin plate as well. So those are kind of the basic ideas. And so today we are going to wrap up the discussion about the reflection the models with the microphase set models. And after that, we are also going to discuss some other kind of components about the rendering, including some the camera measurement and the color as well. So the microphase set the model is basically assuming that there are some kind of the tiny, the surfaces that are basically describing some kind of the details of the material the properties. So this is like one of the example that we can see like this kind of the rendering the output with the microphase set is scattering the model. So the basic assumption with the microphase that is scattering the model is that it's basically modeling some kind of the rough surface as a kind of the collection of a small surface patches. So we basically denote the kind of the entire the rough surface as kind of the macro surface, and the small surface patch basically is denoted as the micro surface. And this kind of some distribution of some small patches basically affect the final rendering, especially the reflection and also the transmission as well, based on kind of the variation of the surface number. So here basically some of the assumption is that we are basically assuming that the perpendicular the projection of the micro surface basically covers the macro surface as well. So this is basically some of the notation that we are going to see over the rest of the slides. So when the omega here basically denotes the surface number, the microphase at the surface number at the point P, we can see that basically the sum of the projected area with respect to the kind of the number of the macro surface becomes the same as kind of the the area of the macro surface as well. So this is kind of like basic thing. So the couple of things that we are going to see in this kind of the microsurface the scattering model is that we are going to basically describe some of the characterization of this kind of model as kind of with some kind of distribution the function. So basically the microphase set the distributive function is basically describing the relative the differential area of the microphase set with respect to the surface number of the omega m here. So we see basically describing how many the proportion of the micro faces are basically having this specific the surface number. So basically we have this kind of the relationship describing the ratio of the surface number with respect to the given the surface number. And given the kind of property that we have seen in the previous slide, that is the projected the area of the micro face that should be the same with the area of the macro surface, we can basically see this kind of the normalization the constraint. So all the kind of the micro face that this function d here should basically satisfy this property. Makes sense? So from this, like one thing that I can ask would be is that what would be basically the microphase that the distribution the function for a perfectly smooth the macro surface. So when we know that the macro surface has the surface number the n vector here, it does not have any kind of the bumpy kind of things, but it's perfectly the specular the surface. And then what should be basically this microphase set the distributive function in this case. So check out the definition of the microfacet distribution function, which is basically describing the proportion of the microfacet that has some certain the surface number, the omega m here. And if we assume that the surface is perfectly, smooth the surface with some kind of the zero bump, perfectly flat, then what should be the microfacet distributing function in this case? Well, yeah, in this case, basically, we can say that the output of this distribution function should be 1 only when the omega m becomes the same with as the vector n here, right? Otherwise, it should be 0. So we can basically represent this function as kind of the Dirac delta function. Yeah. So the output should be basically Dirac delta function, taking the difference between the omega m and the vector n as the input, right? Yeah, so that's basically the way that we are defining the properties of the microfacet models. So there can be some multiple ways that we are defining this kind of the microfacet distributive function. There can be, I mean, there's be many kind of the some different ways. Actually, this kind of discussion has started from the 1960s, and from that time, actually, there are some kind of the multiple the models that people are proposing. So this one was basically the oldest one. The Beckman Spicino distribution was introduced in 1963. So we are going to skip some of the details in terms of how we exactly derive the formulation. But this specific distribution was defined based on that we are assuming that some of kind of some bumpiness of the surface is defined based on the Gaussian distribution of the microphase at the slopes. So when you basically define somehow consider some sort of the Gaussian distribution of the microphase at the slopes, we can define the distribution as like this. So we can control some kind of some parameters, the alpha here, in terms of like having some sort of different kind of the models. The other also the famous model is the Trowbridge, the Wright model, which was introduced in the 1975. And the same model was also reinvented in the 2007 as well. So which was also called the CGXD model. So those are also the cases that the microfacet, the model is basically the case that we are somehow representing some kind of the macrosurface as kind of the loss of some kind of the ellipsoidal bumps. For those kind of the cases, we can also see this kind of the distributive function, which can be also controlled by some kind of the parameters, the alpha x and alpha y here. So those are some of the kind of the some specific cases of defining the microfacet, the distributive functions. And these are some of the different images that are rendered with some kind of the different the distribution functions. So can you see tell some difference between these two? So you can see some kind of I guess, yeah, I hope that you can somehow tell some kind of the properties of the materials here, having some sort of it's not exactly seeing some kind of the bumps. So making some of the bumpy kind of the images that we can also see, but it's basically having some kind of literally some tiny, some micro kind of the small patches that only just the effects in the kind of the reflection the models with some kind of the variation of the surface numbers, right? So depending on the parameters that we are varying, we are seeing some kind of the different effects of like having the microphase at the models, right? So here basically we only saw that how this kind of the distribution can basically vary the normal direction at each point of the surface. But the thing is that if we also have this kind of the bumps over the surface, the other thing that we also need to consider is basically some kind of the occlusion because like one microfacet can basically occlude the other one, right? So that will also affect some of the outputs. Basically to approximate all this kind of the effect of this kind of the masking, like occlusion of like one microfacet by the other. The Bruce Smith was also the person who basically introduced some of these approximation deformation to model this kind of the masking, which was also introduced in the old time, the 1967. So in the Smith approximation, there are some couple of some kind of things. The first thing is that we are assuming that we are only seeing a subset of the microfacet, which is visible from each of the view. But we obviously, when you see some the specific the macro surface here, we are only seeing some kind of this kind of the projected region as kind of the visibility area. So this will be basically the subset of the microface that will be visible from each of the view. And also the thing is that the microfacet can be demasked out because some kind of the back facing. So especially if we have this kind of the microfacet, I'm not sure whether you can see my the mouse, the cursor. For those kind of the microfacet, which the normal is basically on the heading to the back side with respect to the view direction, those will be basically somehow occluded, right? Basically not visible from the view direction. And also some of the microfacets can be occluded by the other microfaces. So this is basically some kind of like changing our some kind of the normalization, the constraint deformation into this form. So this is the specific case when you basically pick the omega as kind of the view direction. So this is kind of the more general case without considering any kind of the view direction. But when you start to consider some kind of the view direction, which is specified with omega here, then we can say that we can derive this kind of the another deformation. So here, basically, one we can say is that we are assuming that we can only see a subset of the microfacet from this view, which is basically incorporated in this term, right? So we are taking not one, but the cosine theta here. And also some of the microfacet, which is basically somehow like the mapped out because of the backface decalling is basically also the incorporated by the taking the max here, right? So if the degree between these two directions is greater than the 90 degree, then we just ignore those kind of the microfacet. And also to model this kind of the occlusion of the microfacet by the other, we are introducing another term, the G term here, which is basically describing the occlusion across the microfaces. So this is kind of the another some kind of the condition that we are considering for the definitions of the microfacet, the distributive function here, D here. And as you can see, what you can see is that once we define the distribution function D here, then from this kind of the constraint, then we can also derive this kind of the masking the function G1 as well. So that's basically what we are going to do. But obviously, this computation is quite complicated, so we are going to also introduce another one more kind of the assumption, which is basically assuming that the height and the normals of the different points over the surface are basically statistically independent, which is basically a very strong the assumption. This is assuming that each of the macro surface is kind of the soup of all the small some of the small patches. Without really thinking about how those kind of patches will be connected to each other. Just having a kind of soup of the small patches. So when you have this kind of the very strong assumption, that we can also assume that the masking is basically becoming independent of the microsurface that normal, which means that now we can remove this kind of the omega m term here because we are assuming that the masking becomes independent with respect to the microsurface normal. Then we can take out this G term out of the interior like this. So this is basically the Smith approximation that was introduced in the 1967. And then what we can do is that for each of this function D here, that we can really calculate this masking function here, the G term. So we are not gonna basically work on basically how we can exactly derive those kind of things. But it's kind of like one case, like if we take the Trowbridge, the Rice knot model as kind of the microphase set, the distribution function the D here, then the G can be solved like this. So G can be derived as kind of this kind of equation. So this is also the basic idea. Then if we have any kind of the microphase that the distributive function, then we can also derive the masking function like this. Make sense? Any questions on this? And also one more thing is that the masking function is basically describing the flexion of the microphases that are basically visible from each of the direction, the omega here. So if we compute this masking function for the outgoing direction, the omega r here, that becomes about the computation about the masking, how much of the fractions of the microphases will be occluded, basically not visible or visible from the outgoing direction. But if you also compute the same thing, the masking function, not about the outgoing function, but also for the incoming direction, that is also computing about the shadowing, how much of the microfaces will be basically shaded by the lights due to some kind of occlusion. So what we basically going to do is that we are going to define this kind of the joint, the masking and the shadowing term, which is basically assuming that this like the masking and the shadowing are basically statistically independent events. Now we can simply multiply these two, which is basically now incorporating the masking effect from the outgoing direction and also the shadowing effect from the incoming direction as well. So once we basically define the microphase that the distributive function D here, then based on that, we can compute the G function, which is about the masking. And then we can take this masking function both for the outgoing direction and the incoming direction. Then we are basically incorporating both the masking and the shadowing effect in our basically the rendering equation. So that's basically what we are going to do. And this is kind of the effects of the self-shadowing. So when you also incorporate the shadowing as well from the incoming light direction, then we can see this kind of the difference that we are having some kind of the shadows in some bumpy area like this. Makes sense? So yeah, we basically discussed some kind of the basic idea that how we define the microphase model. So basically what we are going to do is that based on all this kind of some assumption and also the definition that we are modeling the microphase at the surface, now we are going to derive a BRDF with this kind of the model, which was also basically the idea that was introduced in the 1967 from this part of the model. So here, basically, there are some couple of also the assumptions. Basically, we are also assuming that a surface, the macro surface, is like a collection of the perfectly smooth, the mirrored microphase set. So when you consider every single the microphase set, we are assuming that those are basically the small patch. We are having the perfectly specular reflection, right? So given this kind of the assumption, what we can say is that in our BRDF, basically, if we specify the incoming and the outgoing the ray direction, then we only need to care about the microphase set that has the half angle vector as the surface number. Does it make sense? So what we need to see here is that if we have in the BRDF, we basically specify the incoming and the outgoing direction, right? So maybe this my pen here. Yeah. So if we specify the incoming and the outgoing direction, then only the subset of the microphase set that has this vector as the surface number will basically reflect some of the lights from this specific incoming direction to this specific outgoing direction, right? So it's a matter of like basically calculating the proportion of the microphase set that has this half angle vector as kind of the surface number. And this half angle vector can be computed as kind of some sort of the geometric mean of these two vectors. You see, so we're having this incoming and outgoing direction, and this becomes the half angled vector. That only this microphase set that has this number vector as the surface number will basically reflect light from this specific incoming direction to this specific outgoing direction. And this is some kind of the diagram, which is basically showing some kind of the examples. So when you have like this specific outgoing direction, every time when you vary the incoming direction in this like the range of the green the area, we are also having this kind of the half edge, half angle vector, the distribution like this. So here, basically, in this kind of figure, green shows the kind of the region, like the distribution of the incident diffraction, and the purple region is showing some kind of the corresponding the region, showing the distribution of the half angle diffraction. Makes sense? So when you have this kind of the outgoing direction, every time when you basically make some kind of the perturbation of the incident direction here, then we're gonna see that the angle vector is basically varying over this kind of the purple area. Some kind of the visualization of their kind of the relationship. Clear? So based on that, we are going to derive the transport model introduced in the 1967, which may not be that kind of the precisely like some kind of accurate, some physical kind of some kind of model, but we're gonna basically see how we can somehow make some kind of the assumption here. Based on kind of the ideas that we have discussed in this course so far. So basically, by definition of the radiance, the differential the flux can be defined like this, right? So actually, the radiance was defined as kind of the flux, differential flux over some kind of the differentiable, the solid angle and also differential the projected area, right? So this is basically by definition of the radiance. This is also incoming the differential difflux, which is defined the same way. But now we want to consider only the subset of the microfacet that has the this half the angle vector as the surface normal, right? So we can rewrite the incoming differential flux like this. And what will be kind of the relationship between the incoming differential flux and the outgoing differential difflux? So basically, the proportion of the outgoing differential difflux with respect to the incoming differential difflux will be basically described with the Fresnel coefficients that we discussed last time. So this is kind of only the proportion that will be reflected over the surface. We also having another portion of the light which will be refracted, basically transmitted inside the material, right? And we are also incorporating the joint demasking and shadowing term here as well. So now we can see that the relationship between the outgoing differential flux and the incoming differential flux can be represented like this by incorporating both the Fresnel coefficient and the joint demasking shadowing term. Right? And also by definition of the the microfacet distribution, which was describing the relative differential area of the microfacet with the surface number of the omega h here, which we can also rewrite like this. And let's say the BRDF is now defined like this, based on the definitions, right? So by incorporating all these kind of the components that we have discussed so far, can you now derive the BRDF term? So this is basically nothing but just like rewriting this BRDF the function with some kind of the some equations that we are seeing in this slide. So to save time for some discussion for the paper presentation, let me just go over with the next slide. I recommend you to basically derive the formulation yourself after the lecture. This will be basically quite straightforward, basically just rewriting everything with respect to the basically the BRDF the function here. So basically, if you substitute many of the terms here with the kind of the other things, then you'll be able to see that actually now the BRDF can be derived like this. This is basically nothing but just rewriting everything with respect to the BRDF function. Then you get like this kind of the term. But when you have this kind of equation, you can see that you are having the ratio between the differentiable solid angle for the half the angle vector and the differentiable solid angle for the outgoing direction, right? And what we are going to see is that this kind of the ratio between these two can be also substituted as kind of the 1 over the 4 times the cosine the zeta h here. This zeta h is basically the angle between the outgoing direction and also the half the angle vector. It should be also the same with the angle between the half angle vector and also the incoming direction. So if we also further replace this part into this equation, then we can basically derive the final this parallel model like this. So here basically what we can see is that once you define any kind of specific model for the microphase set the distribution the D here, based on this microphase set distribution the D, now we can derive a masking function which is the G term. And also this kind of the joint, the masking, the shadow term is basically also derived as kind of the multiplication of the two masking the function, both for the incoming direction and the outgoing direction. And based on that, you can now derive the BRDF as kind of this form. So this is kind of the equation that we can see, which is basically independent of the choice of the microphase and distributive function D here. So whatever the distributive function D here you have, based on this D, now you can compute the G function, the joint masking shadowing function, and also derive the BRDF function like this. So which means that you can basically using this transparent model, you can just like plug in any kind of the microphase and distributive function D here. So yeah, I'd like to recommend you to basically check this out yourself. And also one more quick thing is that if we see why we have this kind of thing, one easy way that we can basically derive this kind of formulation is that if we also consider a speaker coordinate system, which is taking the incoming direction, the omega I, as the z-axis here. So if we see that like this, the z-axis is the direction of the incoming direction. We basically set up this kind of the specific speaker coordinates, then we can see that the omega r, the outgoing direction, when this like the omega r, the outgoing direction is represented as this kind of the azimuth, the elevation like this. We can see that the half angle vector, the omega h, is now becomes a vector which is sharing the same the azimuth while taking the half of the elevation, this theta here, right? So when you see this kind of the relationship between these two vectors, and also when you see that this kind of the differentiable, the solid angle can be basically replaced as kind of the sine zeta, the d zeta, the d pi, then basically based on this kind of effect, then we can basically derive this kind of formulation. So let me just go over through like those kind of things. We basically rewrite like this, showing the ratio between these two. We can basically rewrite these kind of parts based on the fact that the half angle vector is now represented as the half of the elevation and also the azimuth here, right? Now we can basically write that this kind of the ratio between these two can be also described as kind of the 1 over 4 times the cosine of the zeta h. So yeah, we are just like skipping some details here, but I also recommend you to check out those details in the slide after the lecture. So this was kind of the very specific the model of like describing the one of the microphase at the kind of distribution. But also there are tons of the other kind of the ways. So this was kind of the model that we are seeing here, which was introduced in 19 67, but there are also many other kind of some theoretic models, as you can see here, and also even there are some kind of the empirical models as well. And also one kind of big thing that we did not discuss in our the class was basically how we also capture this kind of the BRDF from some kind of the materials of the some real the objects. So there are also kind of the some kind of the ways that we can capture this kind of some material the properties from the real the objects. So you can also even check out some of the kind of the database that you only describe some different kind of the material the patterns like this. So there are some kind of the famous the BRDF, the databases, the MER, the BRDF, the database, the MERA, the BRDF, the database is one of the famous kind of the databases for the BRDF as well. And also there is also another the famous the material the database from the EPFL. So you can check out those kind of things if you want to utilize this kind of material properties in your the rendering pipeline. So those are kind of the some wrap up of the refraction the models. Do you have any questions on this? Yeah, so I skipped some details in the formulation to save some time. But I recommend you to check this out after the lecture. I'm also going to post all the details of the slides in the course web page. So before we move on to the next topic, I'd like to show one more thing, which is about the subsurface scattering, about the BSSRDF. So we were discussing the BRDF. So now this is about like BSSRDF, which is about like bidirectional scattering surface reflection distributed function. So which is all about the subsurface scattering. So there are some specialty types of the materials that we are also seeing some kind of the cases that the light basically also pass through the objects and undergo some kind of the some reflections under the surface and basically popping out from different the point of the surface. So this is the case that we are also seeing some kind of the subsurface scattering. So we are not going to discuss any kind of some technical details about the BSSRDF, but we are going to mostly just see what of the kind of the cases that we need to have this kind of some specialty models. So typically when we have some kind of some translucent materials, having some kind of this kind of some very dense liquid, or some of the cases that when we have some kind of the multiple layers in our kind of the material, we might consider having this kind of the BSSRDF, having some kind of the subscattering the properties. So these are some kind of the different rendering the outputs that when you just use the BRDF function for the milk, but when you also use the some surface scattering the models like this, we are seeing some kind of the more realistic the rendering the outputs, which you can modeling that the light basically can pass through under the surface, but basically popping out from the other the points, right? What will be some kind of the other kind of the examples that we also need to have some kind of the subsurface scattering the models? One of the most important examples that we need to have this kind of model is for the human skins. So when you have some kind of the classical the rendering the models, typically we get this kind of some plastic like kind of some natural the feeling because like the BRDF cannot properly capture all these kind of the material properties of the human skins. But typically, the human skin should be basically represented as some kind of having some multiple layers. So the light can basically penetrate through some of the layers, but can be also reflected in some kind of the intermediate layers of the materials. So those might be some kind of the cases that we are also seeing some kind of the subsurface scattering. So when you start to have this kind of the more complex models with the subsurface scattering, we can also represent some more details of the human skins with some more realistic outlook like this. So as I said, we are not gonna discuss all the details about the BSSRDF, but basically the first idea was introduced in the 2001 in the security paper. So I also recommend you to check this out. So this was basically the first paper, as far as I know, describing this idea. And after that, it also immediately affected in some kind of the industry, the graphics industry, in terms of like making some more realistic models. So the basic formulation is that now we are defining the ratio between the extant, the differential irradiance to the, not the instant differential the irradiance, but the instant the differential the flux. Because we are also going to take the integral not only over the solid angles, but also over the area as well. So now we are taking the 6 parameters, basically 3 out of them is basically about actually 8 parameters. Yeah. So basically having some kind of position and the incoming direction, and also the outgoing the position and also the outgoing the direction as well. So we are taking basically this for the kind of the types of the values, and then the final the radiance for each of the specific the position and also the outgoing the direction. The radiance is basically computed by taking the integral over the solid angles, but also the area as well. So this is basically the basic formulation. So while basically skipping some of the details about the BSSRDF, if I just show some of the effects, like having this kind of the subsurface scattering. So this was also very famous work in the 2010 that started to make some kind of the more realistic the human skins. So now you can see that some kind of some wrinkles, some details of the human skins, and also some more the details about some reflection over the human skins can be better represented with the subsurface scattering. So this was shown in the 2010, and also this is even like seeing some outputs that we are seeing in the 2015. See, like some more the details are way more realistic. So to show some kind of the more interesting outputs, let me quickly also share some of the video showing some of these results. Can everyone see the video? So did you watch the video? Yeah. So this is basically the output based on the subsurface scattering. So it is also like huge topic that we might also need some more like a few more the lectures to discuss all the details, but we are running out of time, so let me skip some of the details. But actually, this was basically a technique that also immediately affected in the graphics industry. So I'm not sure how many of you know the Pat Hanna. Do you guys know Pat Hanna? Kind of the legendary the researcher in the computer graphics. Also, Pat is also the winner of the Turing Award in the 2019. with his kind of the pioneering the work in the computer graphics. Actually, many kind of things that we are discussing in this course is based on his work in the 1980s and 1990s. And actually, as far as I know, he's the kind of the winner of the Turing Award as kind of the second time in the computer graphics. The first time winner of the Turing Award in the graphics was someone in the 1988. Do you guys know who is the first the person in the computer graphics who won the Turing Award? 1988. No idea. Ivan Sutherland was also another the pioneer who won the Turing Award in the computer graphics in the 1988. As far as I know, like those are only the people who won the Turing Award in the computer graphics. Ivan Sutherland is also kind of some early pioneering researcher that is basically also introduced many kind of some basic concept that actually we discussed in the introduction to computer graphics course. So yeah, and also the Pat is also one of the billionaire, is kind of the co-founder of the Tableau as well, and also the founding employee at the Pixar. Among his many kind of achievements, actually, he's also the winner of the Academy Awards with some technical contribution in the computer graphics. So he actually awarded the Academy kind of awards for the 3 times. One with his basically the RenderMan, which is the rendering software developed by the Pixar, and one is based on the physically based rendering the book that I'm basically referring to in this like lecture. This book. So I recommend you to also check out this book. This is the book that also describes all the details about this kind of the rendering pipeline. And the good thing is that the content of this book is now publicly available. So even you need to buy the book, check out the book website with some more details. And one of the kind of the academic awards that he basically received was based on his work about the subsurface scattering with some kind of, because the first idea was introduced in the 2001, but it immediately basically used in the many kind of some movies and the films. Can you guess what would be kind of the films that was using this kind of the subsurface scattering technique? The Lord of the Rings, the Gollum was the character that was also rendered using the surface scattering, and also many of the characters in the Avatar was also used as known as kind of the rendered as kind of the using the subsurface scattering technique. And this is also the comparison between the two cases that rendering the same scene without the subsurface scattering and also with the subsurface scattering in the Ratatouille by Pixar released in 2007. So you can see some kind of tell the difference. So the left one looks more like some kind of the plastic kind of things, while the right side one is basically more looks like some real food. So you can see this kind of the difference. So if you are also interested in the subsurface scattering, I recommend you to check out some more details in some past paper or some other the papers in the 2000, and also you can check out more details in the paper book as well. So this was kind of some very quick kind of the intro for the subsurface scattering. And as kind of some last component of the ray tracing, while there are tons of some technical kind of components that can be incorporated in the ray tracing the system, as kind of the last component to see how exactly we get the final image in the ray tracing system. Let's go over with the camera measurement and the color system. Before we move on, any questions? So I'm also gonna go quickly with this kind of the topics, and especially for the color, we also discuss some details in the introduction to computer graphics the course. So if you are more interested in some more details, I recommend you to check out the CS380 course. But we are going to quickly basically go over with some of the ideas there. So basically, as I also mentioned in the previous lecture, so once we have this kind of the path tracing, BRDM, or the reflection in the system with the ray tracing the framework, how we gonna exactly calculate the final image? Basically, how we can also determine the color for each of the pixel? This is exactly what we are going to do, right? So we did not discuss some details, those kind of things. So let's get over that. So as I also briefly mentioned in the previous lecture, what we are doing at the end in the rendering the system is that actually we are computing the radiance at each of the pixel, basically in the plane. The radiance will be basically computed in this kind of the formulation. But actually, what we exactly basically measure using some kind of the photographic film or the CCD or the CMOS sensor in the digital camera is basically capturing the amount of the radiant energy over some small area for each of the pixel. Which means that to precisely get this kind of information about the radiant energy, we need to take the integral over the radiance over the sensor, the pixel area, and also the time range as well, by definition, the radiance, right? So to get the power information, basically we need to compute the integral over the radiance over the area over the surface and also the time. Well, obviously, if we assume some kind of the uniform the surface area for each of the pixel and also the same amount of the time for each of the pixel, then we can consider that irradiance is some kind of the property which is basically proportional to the final the radiant energy that we are computing, right? So this is basically what we do as kind of the final step of the rendering. But here the question is that how we exactly get the RGB, the color information for each of the pixel. So what we are going to do is that basically all the radiometric quantities that we are defining, some kind of radiant energy, radiance or the radiance, those things, basically all the quantities basically generally vary as the function of the wavelengths, right? Which means that actually we need to compute the quantities for every sample of the wavelengths. Then how we can basically define some kind of the virtual scene where we can basically get some kind of the pixel, the color information. Obviously, the simplest kind of way is that we are basically defining all the quantity for each of the RGB channel. So if we have the RGB, the 3 channels for the color, then we can define all the quantities as kind of the 3-dimensional vectors. Then we can basically also get final the radiant energy for each of the channel. So that can be actually the simplest way that we are making some kind of the ray tracing the system, right? A slightly more like basically the accurate way to calculate all the things would be basically having this spectral rendering, which is also the technique which is used in the PBRT, the code in the PBRT book, the textbook. So basically what we here do is that now we are having the samples of the wavelengths. And then we compute the radiant energy for each of the sample of the wavelengths. And then we determine the final color with the color match function that we are going to discuss in the next slide. So basically what we do with the spectral rendering is that we are not just having the RGB3 channel to define those kind of the quantities, but we literally basically sample the wavelengths and then basically define all the quantities for each of the sample of the wavelengths. And then the final color is determined based on the distribution of like those quantities over the wavelengths. So this kind of the distribution of the radiant energy defined with some kind of the over the wavelengths will be called the spectral distribution. Then here the question might be is that like, why do we need to do the spectral rendering? So basically, as we have seen in the previous lecture, all this kind of the BRDFT function can vary depending on the wavelengths. We also have see that many kind of things like the fresnel, the coefficient, many things can be changed over this kind of the depending on the wavelengths that we are having. So these are some of the examples that depending on like the wavelengths, we are seeing some kind of the different kind of the outputs and also the BRDFT functions. And also the more important thing is that the color is not defined as kind of the quantity for specific sample of the wavelengths, but actually the color is defined as kind of the integration over the multiple the wavelengths, the samples over the wavelengths, the domain. So that's kind of thing. So to get some kind of the color information more like basically accurate way, we are going to basically have some multiple samples of the wavelengths and having the radiometric quantities for those kind of samples and take some kind of the interval to determine the final color. And also one of the kind of the assumption in the spectral rendering is that fully we can easily assume that the light in the different wavelengths are basically decoupled, which means that the energy that we are calculating for specific the wavelengths will not basically affect the energy that we are calculating for the another the wavelengths, which means that this kind of the computation, like all these kind of the radiometric quantities can be computed for every single the wavelength the sample as kind of like independent way. So without any kind of the some effect across the wavelengths. Some exceptional case is for the cases of the fluorescence the materials. For those kind of the cases that the energy can be redistributed over the different the wavelengths, those will be the cases that is kind of the reflection the effect actually should be encoded with some kind of the n by n the matrices when the n is the number of the spectral samples. So this is kind of the complicated the cases that we need to somehow consider how much amount of the light energy is basically transferred from the one wavelength sample to the another the wavelength sample. But except for those kind of cases, we are going to assume that all the radiometric quantities are basically calculated for each of the wavelengths sample. So that's the basic idea. Then how exactly the color is basically calculated. So basically each of the color is basically defined as kind of the color match function. So when the S, the lambda here, is the spectral distribution, basically the radiant energy that we are calculating for each of the sample of the wavelengths, then we can basically take the integral into this form with this kind of the coefficient function, which is the color match function here. And depending on how we define this match function, we are defining the kind of the property of each of the color. And we can calculate the final color by taking this kind of integral, right? So here, the quick question is that how can we calculate this kind of integral in our the ray tracing system? Well, I mean, the answer is basically Monte Carlo estimation, right? For all the integral can be computed with the Monte Carlo estimation with some kind of the importance sampling. So we can do the same thing. We can do some kind. We can sample some wavelengths based on kind of the probability distribution and calculate all the thing, and then we can take the final the integral as kind of the Monte Carlo estimate. This is kind of the example of the color matching function, which was basically introduced in the 1931. So this is kind of the first work of like introducing some color matching function. And then after that, there are some kind of the many other variations that we could see. So here, the interesting thing is that even the color matching function goes to the negative values, right? So if you are interested in like why we are also seeing some kind of the negative the coefficients as well, I'd recommend you to check out the CS380 course, which was the case that we also describing some more details about the color matching function. So basically all these kind of some color spaces can be represented as kind of the combinations of the color matching function. And obviously, as you have some more samples over the wavelengths, we can see that there's a more realistic and more accurate the outputs, as you can see in these kind of cases. But obviously, as we have some more these samples, it does not really affect the some kind of the accuracy at some kind of point. So in this specific example, if we have some more than 8 number of the samples for the wavelengths, then you can see that actually the difference is basically quite marginal for those kind of cases. So depending on some kind of the complexity of the scenes and also the lighting and also many other kind of things, we can consider the number of the wavelengths, the samples to get the final outputs. So in the code of the PBRD book, typically people use the full samples of the wavelengths as kind of some kind of default number, but you can increase the number of the wavelengths samples to the 8, 16 to 32 as well. So this is kind of examples. And also instead of like having this kind of the RGB the color spaces, you can also consider rendering the final the image into different color spaces. So those are some of the examples that you can check out as kind of like different color spaces. And as I said, all these color spaces can be basically defined based on the color matching function. So this is the way that we are defining some color spaces. So here, like one specific, very special class space is basically this XYZ class space, which was basically also invented as kind of the first class space model in the 1931, which is the case that is kind of like following the human color perception. And the thing is that this XYZ color space is now being used as kind of the base color space for almost all the other color spaces, which is also specially defined like this, somewhat normalized with this kind of the white term here. And the reason why this like XYZ color space is like being used as kind of the basis of the other color spaces is basically this property that the input, the spectral distribution can be approximated as this kind of the linear combination of like those kind of things. So this is kind of the very special properties of the XYZ the class space that we are taking this assumption for like some kind of the almost kind of the some several decades to define many other kind of the class spaces. So from this specific property that we can approximate the spectral distribution as kind of the linear the combination, what we can do is that we can do some kind of the conversion across the color spaces. So this is like one specific example, like how exactly we convert the XYZ color space into the RGB color space. So if we basically substitute the spectral distribution here as kind of linear combination like this, then we can see that this like a vector with this three-dimensional vector with the XYZ value can be basically mapped to the another three-dimensional vector describing the RGB the color value. And you can say that like all these kind of the terms can be pre-computed based on the definition of the color matching function for each of the channel. So which means that all this kind of some three-dimensional vector describing the color in each of the color space can be mapped to the color in the other color space using some kind of the 3x3 matrix. So you can check out all these kind of some kind of mapping from the one color space to the other color space, and many of the color spaces can be basically mapped through the linear mapping like this. So you can also check out this website to see how exactly this kind of conversion was defined. And also the one final remark is that also different color spaces also cover different ranges of the color, which means that there can be some of the color spaces that are basically having some kind of the larger the range than some kind of the colors that are visible from the human eyes for those of the cases. So what we can see in this kind of figure is that each of the triangle basically represent one of the color space. So when you have this kind of the big triangle, this is the case that the color space even can represent some of the colors that are not visible to the human eyes as well, right? For those kind of the areas here and also here. This is kind of the area where basically the color spaces can represent the color, but those are the colors that are not visible to the human eyes. Also for some of the other cases, we are having some smaller triangle. For those cases, this color space may not be able to represent some of the colors that the humans can see. So basically here the idea is that how we are basically defining some kind of the exact color space that can basically cover the visible color areas as much as possible while not taking too much kind of the some regions that are basically representing some invisible colors. So those are basically the basic ideas for the color spaces. Any questions on this? So yeah, I went through those details quickly to basically discuss some more the topics. So next time we are going to discuss the neural rendering and also the volume rendering as well. And then we're also going to move on to those kind of some more neural rendering topics next time. So if you also have any questions on this, please post the questions on this Slack. And let me